So we've seen in previous chapters that stars of different masses leave different types of stellar corpses, like the low mass stars, like the Sun. This one leaves behind white dwarfs when they die. They go through subgiant phase, giant, the helium flash, remember, horizontal branch, and then the red giant, and then some pulsations. One of them is going to turn out deadly. And then you have the planetary nebula phase. That is an explosion. It's going to, the star ejects the outer layers, leaving behind this white dwarf. And what's going to happen after the explosion, that basically carbon star is going to simply cool off. So it's going to move toward lower temperature in this HR diagram, which has luminosity or brightness and the temperature that increases this way. All right, so basically it's going to cool off and grow dimmer, right? So this is the trajectory. It goes towards lower temperature and towards fainter magnitudes brightness. Okay? All right. Other things we talked about were so that besides their definitions, so they're basically the remaining course of dead, I would add small mass stars. Okay? Another important thing to remember about these white dwarfs, often referred to WD, is that they are supported by degeneracy pressure, electron degeneracy pressure. So basically, all the atoms, all those carbon atoms are pushed together into a very dense material, carbon atoms. But basically, electrons are kind of roaming around, okay, and it's that roaming, it's that tendency for the electrons to find their space while also finding a certain energy that they call theirs, that creates that pressure that doesn't have anything to do with the temperature, but that is the pressure that motion of electrons is going to keep up with the gravity, because gravity always works. Every time you have matter, matter is going to push onto one another. All right. Another thing I wanted to talk to you about is that you actually know one white dwarf out there in the sky, which is the Sirius star. Seriously, that is the brightest star in the night sky. So, Sirius. In the night sky. So you can see it with the naked eye. But it turns out Sirius is a binary system. A binary star. So there is the A component and the B component. Now, nearly all the visible light that we see from Sirius comes from Sirius A. But when we photograph the system in X-ray light, this is a Chandra X-ray image here of that binary star that's called Sirius. What we see is actually, so this is B, the brighter one in X-ray, and this is Sirius A, which is the one that's dimmer in the X-ray emission, right? So in terms of how much X-ray is emitted out of those stars. So again, in the visible, Sirius A is actually the main sequence star. It's actually of a spectral type A, and guess what? Sirius B is a bright white dwarf. Okay, so this is a white dwarf, and this is a main sequence star. I think you're going to look at Sirius now with different eyes. So, the dwarfs, they have some really interesting properties. Like, for example, you take a white dwarf that has as much mass as the sun, and guess what? Its size is going to be about the same size as Earth. Okay? So now, fun fact. The mass of the sun is about 1/3 of a million times the mass of the Earth, right? So that's about 330,000 Earths in terms of the matter that they comprise, right? So imagine multiplying this by, I don't know, something like this number, and it's kind of crazy. You get something of the same size. Why is that? Any guess? Well, the white dwarfs shrink as you add mass because their gravity gets stronger, right? So you add another layer of matter on this one. Well, that's going to make the force of gravity that's pulling from all directions even stronger. So we have add mass, and you're gonna end up with an even smaller size. Crazy. And also very, very important to understand what other things happen to the white dwarfs. So, a few words about the shrinkage of these white dwarfs. As it turns out, there is a limit as to how much matter you can dump onto the surface of a white dwarf. So, what do we have here? You add mass to a white dwarf, that is going to increase its gravity. That means also we're forcing the electrons into smaller and smaller spaces. Now, to avoid being in the same state, energetic or physical, some of those electrons need to move fast or faster and faster. The more matter we add on the surface of that white dwarf. So, it turns out there is actually a limit to how much you can shrink a white dwarf, right? Basically, to how much you can shrink a high number of electrons, okay? And that is because nothing can move faster than light. Remember that speed of light, 3 times 10 to the 8 meters per second. And when the electron speed approaches the speed of light, right, they're going to tend to move even faster, then that electron degeneracy pressure can no longer support it. And what's going to happen? And there is a limit that Chandrasekhar found actually at the age of 20. He got the Nobel Prize for Physics. Much later on, there will be an explosion. All right, so let's talk about some things that happen with the surface of Earth. All right, so we're going to start with thinking about what happens with the stars when they live with close companions. And because that in that scenario, actually their lives can follow some different paths. Okay, take this Algol star for example. So, an example, we have a binary star. You see here 2 stars, but we measure their masses and we measure how far away they are, and we measure some things about them, temperature, position, and we found out that there is a 3.7 times the mass of the sun main sequence star, and then a sub-solar in mass subgiant star. Do you find anything strange about this pairing? I'll tell you what is strange. This is strange, right? We would expect a subgiant to be more massive than a main sequence star. And that clearly is not the case here. Okay? Why? Because more massive stars evolve faster, right? So if it is already a subgiant, it should have been more massive than the main sequence star. Okay, so now the question is, how did this system came to be like this? Here's what happened actually. So these stars in Algol are actually close enough that matter can flow from one to the other. Okay, so the star that is now a subgiant was actually originally more massive and therefore evolved into a subgiant as expected before the lower mass star that was a main sequence. However, as it reached the end of its life, right, and it started to grow, being a subgiant, right, it grows in size, it becomes even closer to the companion main sequence star. And then it's easier to have that mass transfer that is going to happen now, right? So here is the subgiant. This was a more massive main sequence star, okay? And this now becomes, starts to transfer mass on the initially smaller mass main sequence star. So this one grows in mass and then becomes more massive than the subgiant. So that is the explanation. And that's thinking to what's going to happen next. So here's what's going to happen next. Eventually that mass losing star will actually become a white dwarf. And the arrow should have been here. And the white dwarf's gravity is actually going to start pulling matter off the giant companion. However, because the angular momentum prevents the matter from falling straight in, that fall of matter is going to happen in a disk-like configuration, right? So it's all because the angular momentum needs to be conserved. That disk is going to, in that disk, there's a lot of friction between the orbiting bits of matter, rings of matter if you want, right? The rings of matter in the disk. And because of that friction, there is going to be a removal or transfer of angular momentum outward, and that it's going to cause the disk to heat up and glow. Okay, so now we have high temperature for the hydrogen that falls onto the white dwarf. Now, you should recall that when temperatures are high, and in this case also pressures are high as well, hydrogen does something. There is higher likelihood to have hydrogen atoms or nuclei close together. And what happens then? Hydrogen fuses into helium. And what happens when it fuses into helium? What's happening when hydrogen fuses into helium? You have bursts of light, right? So hydrogen is falling onto that black hole into this accretion disk, and because it's very hot, where it becomes hotter and hotter with more and more hydrogen falling onto it, that is going to start that hydrogen fuse into helium. And that happens with photons created, gamma rays, photons of energy. Okay, so it's going to be a burst of light, and that burst of light is called nova, because that thing is actually going to look like a new star. So this is what we have here. We are talking about a nova. Okay, so of course that thing was first observed. There were like, so suddenly a star appeared where it was nothing before. Okay, so people knew about the existence of them, but it was only later on, after we discovered the existence and explained the physical properties of the dwarfs and their existence in binary systems like this, that we understood what exactly is that nova. So it's basically accreted gas that lit up because of the hydrogen, a burst of hydrogen fusion. Okay, so it is a burst of hydrogen fusion that is going to release energy, and that white dwarf or the accretion disk is going to cool off for a while. However, right, and what's going to happen? There are, some of that accreted gas is going to be expelled into space for a few weeks. After that, there could be yet another nova phenomenon happening, especially if that dumping of hydrogen from the companion continues. Nevertheless, we already know now, when we learned from Chandrasekhar, that there is a limit as to how much matter, in this case hydrogen, we're going to be able to dump on the white dwarf. And so if that amount of matter is going to reach that limit, then carbon fusion is going to suddenly begin as the white dwarf becomes, that mass of the white dwarf becomes 1.4 the mass of the sun. And what's that going to cause? A total explosion, okay, with nothing left behind. Nothing is going to be a total explosion. So that actually is a very powerful phenomenon, very luminous, and that is, we realized, a new type of supernova. Okay, so that kind of supernova is very, very luminous, especially by comparison with the nova, is at least 10 times, if not more, 10 times more luminous than a nova. Okay, so now compare with a different type of supernova that we learned before, that is actually the explosion that happens at the end of a massive star lives when the iron core that forms in the very center of that star, after it evolves and it depletes all the hydrogen and then helium and then the carbon and oxygen and so on, that onion-like structure with the iron core of that massive star, that is going to collapse. So that massive star supernova or core collapse supernova, or also called type 2 supernova, right? That's a bit different. The explosion itself is actually caused by a shock wave thanks to that collapse, and it does leave behind a neutron star or a black hole if the that massive star was above a certain limit. We're going to talk about that in the next little lectures. So, would you wonder maybe how do we know one type of supernova from the other? So one way to tell the supernova types apart is by looking at how the brightness or the luminosity changes with time. So at the beginning, they are pretty luminous and they fade in time, but their fading is different, and also the white dwarf supernova is usually brighter than the core collapse or the massive star supernova. And the changes, look, there are some features and some others in a spectra that we're not gonna bother you with those, but there are actually quite a bunch of differences, and we astronomers are definitely looking for them in order to really understand which type of supernova is this. It turns out is actually quite important. Okay, so yeah, so I was wrong. I said before that a supernova, a white dwarf supernova, is actually about 10 times, no, it's about 10 million times more luminous than a nova event. All right, so some other differences. Note that in a nova, the hydrogen to helium fusion process happens in a layer, and the white dwarf is left intact. Actually, that can be repeated as well. As long as you just dump more and more matter, like chunks of matter maybe at a time, and the white dwarf limit is not reached. However, when that white dwarf limit is reached, right? When white dwarf limit is reached, again, that is m, the mass of the white dwarf is 1.4 solar masses, then there's going to be the complete total explosion, that white dwarf supernova. Again, white dwarf supernova, given that we are talking about two different types of supernova. And now it is something really important. All of these things, that is white dwarf supernovae, they are all alike. That is, they have the same luminosity and the same light curve. And that's very important that they have the same luminosity. We can actually use them as standard candles to calculate distances. And they're very luminous, so we can see those standard candles. So we know intrinsically just how luminous they are. And so we compare the intrinsic luminosity that we can calculate based on actually this limit with the brightness, the intensity of the light that we measure on the surface of the earth, and based on that we can calculate distances. Remember that inverse square law. So yeah, pretty important, very important actually. All right, so we are on a quest to find those white dwarf supernovae, because that's one of the most important ways of finding distances to faraway objects, because you just can't take the meter stick and say, okay, put it, just keep measuring the distance to those things. We need to be really creative to find out just how far away these things are. Okay, so it is very important to distinguish between the massive star and the white dwarf supernovae. Their light curves differ and their spectra differ. Even though I didn't show you any example, might be useful for you to know. If you want to ask more questions and look around, feel free to do that.